Hello everybody, in this lecture we will be solving 1994 IMO problem number 5. Here is a view of this problem. Let S be the set of real numbers strictly greater than -1. Find all functions f from the set S onto S such that the following two conditions are satisfied. Let's first start by inspecting if the problem makes sense. So we have a function f which maps from -1 to infinity to -1 to infinity apparently. Let's check if the argument is greater than -1, otherwise it won't even make sense, this condition. So we can, let's write that down first, plus x f of y. That one, we can factorize it as x plus 1 times f of y plus 1 minus 1. Now obviously this expression here is greater than or equal to 0 because f takes the function to numbers greater than or equal to -1, -1 plus 1, so this one is also greater than or equal to 0, suggesting that the whole thing is greater than or equal to -1 as claimed. So the domain, the argument, is within the domain, and so the problem as such looks like it is properly posed. Now let's start by, because it's a functional equation type of problem, we need to test different values. Let's first replace y with x. Then in that case we would get that f of x plus f of x plus x f of x is equal to x plus f of x plus x f of x for x in -1 to infinity, and therefore it looks like we have a fixed point here, right? So for x in this range -1 to infinity, we can simply denote this expression as s, and as a result we have that let s be equal to x plus f of x plus x f of x. Then this implies that f of s is equal to s, suggesting that s is a fixed point of the function f. And now if I apply the same functional equation, this time for s, because, well, s will obviously be, because x is in this range, the domain is in this range, the range will be also in the same range. So s, since s is in the range -1 to infinity, then I can plug it into this reduced expression again, for which case I would get that let me write that down. So we would get that f of s plus f of s plus s f of s is equal to s plus f of s plus s f of s. But notice that s was a fixed point, so this would imply that f of 2s, so this one would come out as an s, so we have 2s plus s squared is equal to, again, 2s plus s squared. But then this is another fixed point, so you can just simply call it as t. So so this implies f of t is also equal to t. So we have found a new fixed point. So t, which is equal to 2s, or I can even factorize it, s times s plus 2, is another fixed point. But now this is troublesome, right? Because now we have found two fixed points, and here let's assume that assume for a moment that s is not equal to 0. In that case, our number t is definitely not equal to s, right? Because it's non-zero, right? So t will be different than s, and as a result, and they will, by the way, have the same sign as well, huh? They will have the sign of t will be the same as the sign of s. As a result, notice that because the function is fixed for s and t, we have that f of yeah, let's just write it like this: f of s is equal to s and f of t is equal to t, implying that f of s over s is equal to 1 and f of t over t is equal to 1. But that clearly violates, noticing that t is not equal to s, this and they are on the same side, they have the same sign, either both negative or both positive. It violates the second condition, f of x over x being strictly increasing, which is obviously not the case here. Even though t and s are not equal, they give f of s over s or f of t over, so the function f of x over x remained constant. So therefore, this assumption, the earlier assumption that s not being equal to 0 was false. So therefore, s has to be equal to 0. And as a result, if you recall the way we defined s here, so this would imply that 0 is equal to x plus f of x plus x f of x. Move x to the left hand side, factor out the f of x. We would get that f of x is equal to minus x all over 1 plus x. And that's the closed form for the function f of x. That works because, and that's the only solution, because to begin, we started with a random choice of x in this range, in the domain, and everything was purely general, so we didn't put any additional restriction on the problem. So therefore, this is the closed form solution, and it's just a simple calculation to show that both of these conditions hold when f of x is defined as such. I leave it to you as an exercise to confirm the validity of these two, to verify that conditions 1 and 2 are satisfied when the function f is defined like this. So hope you enjoyed the video and looking forward to see you guys in our next lecture.